Hi everyone and welcome back to my channel. Why doesn't an electron fall into the nucleus? If you're a student just beginning to learn quantum mechanics or chemistry, this is probably one of the very first questions you've asked. And it sounds like an easy question to answer, but it turns out to be surprisingly difficult. In this video, I'll do my best to explain the answer, but I want to be brutally honest with you from the start. You're probably not going to be completely satisfied with it. And that's because answering this question requires invoking some of the inherent weirdness of quantum mechanics. Quantum mechanics is fundamentally unintuitive, and because of that, we are essentially doomed to fail at producing a simple and intuitive explanation. Still, this question is fascinating, and I'm really excited to explore it with you, so let's dive right in. For the sake of simplicity, let's consider a hydrogen atom. This is the very first atom typically discussed in university courses, so it's a natural place to start. How do we even model an atom? Before the invention of quantum mechanics, the theoretical frameworks available to physicists were classical Newtonian mechanics combined with Maxwell's theory of electromagnetism. The hydrogen atom consists of an electron and a proton, and if we imagine these as two-point charged particles, we can already anticipate what will happen. We know that opposite charges attract, so a purely static configuration would necessarily lead to collapse. The only way this situation could be avoided in classical mechanics is if the system were somehow dynamical. One can analyze this problem using classical mechanics for two particles interacting via the Coulomb force. In fact, the problem is mathematically equivalent to the two-body gravitational problem, except that the interaction is Coulombic rather than gravitational. This is essentially the Kepler two-body problem, but with a Coulomb force, replacing Newtonian gravity. And we know the solutions. There are two unbound trajectories, parabolic and hyperbolic, which are unphysical in this context, because we are interested in an atom, which is a bound system. So the physically relevant solutions are therefore elliptical or circular orbits of the electron around the proton. For simplicity, let's consider a circular orbit and assume the proton remains stationary relative to our reference frame. The total energy of the system consists of the electron's kinetic energy plus the electrostatic potential energy. Now for circular orbits, the angular momentum is constant. If we express the total energy as a function of the distance r between the electron and the proton, we get this expression. And as you can see, it features a clear valley with a distinct minimum. This is a great result because mathematically it suggests that the electron has a stable equilibrium point where it can reside. So from the point of view of classical mechanics alone, it appears that we have found a stable bound solution. However, once we combine this result with Maxwell's electrodynamics, a serious problem arises. Circular or elliptical motion is accelerated motion, and we know that accelerated charged particles radiate electromagnetic energy. And as a result, the angular momentum of the electron is actually not constant. It decreases over time. Consequently, the total energy of this model atom continuously drains away. Watch what eventually happens. That stable minimum point we found earlier simply disappears, and the atom becomes fundamentally unstable. The electron is forced into a terminal spiral toward the nucleus. The only way such an atom could remain stable would be if an external source supplied energy to compensate for this radiation, which is clearly absurd. Atoms are stable on their own and do not require any external energy input. So what classical model therefore predicts is that as the electron loses energy, it would spiral inward toward the proton, and one can even calculate the time it would take for the electron in a hydrogen atom to spiral into the nucleus, and the result is on the order of 10 to the negative 11 seconds. Thus, classical mechanics predicts that atoms are unstable, which is clearly in contradiction with nature. So where exactly is the flaw in our analysis? Well, the key issue is that an electron and a proton are not behaving like tiny classical charged particles. This is the point where we must step outside the realm of classical mechanics and begin talking about quantum mechanics. The first thing to realize is that an electron is a quantum object. What do I mean by that? I mean that an electron exhibits what is known as a wave-particle duality. In classical physics, and in our everyday experience, we are used to objects that behave like particles, such as golf balls, boxes, or cars. These objects are localized, and we can assign them well-defined properties like a position, velocity, momentum, and mass. On the other hand, we are also familiar with objects that behave like waves, such as word waves. These have well-defined wavelengths and can interfere with one another or diffract. Wave-particle duality in quantum mechanics means that quantum objects, such as electrons, protons, neutrons, photons, etc., exhibit both particle-like and wave-like behavior depending on the experimental circumstances. For example, we know that electrons have a definite mass, and we also know that when electrons are detected, they appear as localized packets, or lumps, as observed in experiments like the double-slit experiment. These are clear particle-like characteristics, but at the same time, electrons can interfere and diffract, which are unmistakably wave-like properties. This behavior is also confirmed by double-slit experiments or by electron diffraction experiments. So how do we even describe the objects that behave in this strange way? To describe the nature of electrons correctly, we must therefore abandon the classical idea that objects are either particles or waves. The electron is a new kind of object, a quantum object, which exhibits aspects of both and behaves in a way that has no classical analog. As Richard Feynman famously put it, quantum objects act screwy in their own way. Now I'm going to try to help you build an intuition about wave-particle duality. Let's take a look at the two extremes in this picture. The first extreme is what I call pure wave. For simplicity, imagine a pure wave in one dimension, like a sine or cosine wave. I call it pure because it has a well-defined wavelength. If I ask you what is the wavelength of this wave, you can answer immediately. Just measure the distance between neighboring peaks or troughs. But if I ask you where is the wave, you might think I'm crazy. It doesn't really make sense to ask because pure wave is completely delocalized, it's spread out over all space. So a pure wave has a sharply defined wavelength but no definite position. The other extreme is what I call pure particle. Imagine a sharply localized pulse traveling through space. And if I ask you where is it, you can answer directly. But if I ask you now what is its wavelength, again it doesn't make sense. It has no well-defined wavelength. So a pure particle has a definite position but no clear wavelength. Mathematically, both of these extremes satisfy the wave equation. But the wave equation can also describe anything in between. You can, for example, go from a pure wave to something in between, where the wavelength is no longer perfectly defined. The distance between two neighboring peaks or troughs might be slightly different depending on where you measure them. And at the same time, the wave is no longer completely delocalized. You can't pinpoint its exact position, but you can say roughly where the object is. Similarly, you can start from a pure particle and make it fuzzier, so it is less sharply localized, while also having a wavelength that's no longer perfectly defined. And this is basically what quantum objects are. They can have varying degrees of localization and wavelengths. Interestingly, there is a trade-off between the localization of a quantum object and its wavelength. Basically, the more localized a quantum object is, the more spread out or uncertain its wavelength becomes. Conversely, the more precisely defined the wavelength of a quantum object is, the less certain its position. One can make this idea more concrete with an example. Suppose I have a bunch of sine waves with carefully chosen amplitudes and wavelengths. By superimposing these waves, I can construct a localized peak. You see, by adding together many sine waves, I can create a function that looks like this, concentrated in space, so the position is fairly well known. However, because it was constructed from many waves with different wavelengths, it does not have a single well-defined wavelength. This procedure is exactly what leads to the Fourier transform. I won't go into the details here, but one can show that there is a precise mathematical inequality between the spread in position and the spread in wavelength. Importantly, this is a property of all waves, classical or quantum. There is nothing inherently quantum about it. At the beginning of the 1920s, de Broglie hypothesized that the relationship between the photon's momentum and its wavelength also applies to all material particles, not just photons. So for the quantum objects we've been discussing, this means there is a connection between its particle-like properties, such as momentum, and its wave-like properties, such as wavelength. And if you combine this relationship with the trade-off between position and wavelength that we discussed earlier, you arrive at the precise mathematical statement, the famous Heisenberg Uncertainty Principle. So because of the wave-particle duality and the de Broglie formula, we have derived the Heisenberg Uncertainty Principle. So what about the stability of atoms? Shouldn't this video be about it? Yes, everything we have discussed so far was a necessary prerequisite for understanding stability. I'm going to show this in the case of hydrogen atom because this is the simplest case, but the idea holds for all atoms. This may actually come as a bit of a shock to some of you, and honestly it is still shocking to me, but the mechanism behind the stability of hydrogen atom comes from the uncertainty principle. And we can even derive it. We start by writing down the total energy of an electron in a hydrogen atom. Let's say for simplicity that the proton just sits there in space and doesn't move with respect to some reference frame. The total energy is then the kinetic energy of the electron plus the potential energy. You can think of this expression as a function of a distance between the electron and proton. For this system to be stable, what we need is that this expression for the total energy has some minimum at some point. For example, the potential energy as a function of position looks like this. You can see that it is unbounded from below. But the total energy is not just the potential energy, right? There is also a kinetic part of the energy. Only now we have to express it in terms of position, not momentum, and we can use the uncertainty relation for that. So the kinetic energy as a function of position looks like this. And you can see the strangest thing happening. As the electron goes closer and closer to the proton, its kinetic energy increases, and so does its momentum. This acts as some kind of outward pressure that tries to increase the distance between the electron and the proton. This is not a force in the usual classical mechanics sense, but rather a new kind of quantum pressure. And this is not only the case for electrons in an atom. Remember, the Heisenberg principle is valid all the time. So whenever you take a quantum particle anywhere in space and try to localize it, it will respond in this weird way. Its kinetic energy increases, its momentum increases, and effectively it acts like a pressure against localization. So this is what keeps the atom stable. On the one hand, you have the electric force trying to pull the electron and proton together. On the other hand, you have this weird quantum pressure keeping them apart. As a consequence, the system settles into some equilibrium position. When I plot the total energy as a function of position, you can indeed see that it has a minimum. And can you guess where that minimum is? Well, wouldn't you know, the position at which this happens is the Bohr radius. You can even calculate it by taking the derivative of this function with respect to r and setting it equal to 0. So this is the mechanism behind the stability of atoms. It is the uncertainty principle. At the beginning of this video, I told you that you are probably not going to be satisfied with the answer to the question of why atoms are stable. And this is because one has to accept this effect. When you try to localize a quantum object, it generates this outward pressure that tries to prevent localization. And this is the direct consequence of the uncertainty principle. Nothing in our classical world behaves like this, so I cannot really explain it in terms of something you already know. Anyway, I hope this video was not too confusing and that it at least helped some of you a little. If you have any questions or other ideas for how to explain the uncertainty principle or the stability of atoms in a more intuitive way, please let me know in the comments. If you like this video and would like to support me, I would kindly ask you to hit the subscribe button. Thanks for watching and until next time.